So we've learned about Lewis dot diagrams, and those are really useful for looking at how these different molecules get bonded together. However, they fall short at helping us understand the three-dimensional structure of these molecules, which is going to be very important in order to actually do chemistry with them. Things are going to mix or bond or react based on a three-dimensional structure, as well as all of the things about electrons that we've already learned. So we need to be able to model these in three dimensions. That's where Vesper diagrams comes in. Vesper diagrams are going to allow us to consider what shape each of these molecules would take on. And it's going to do it in a fairly simple and straightforward manner once you understand the process. So first off, let's understand, what does Vesper stand for? So Vesper is an acronym for valence shell electron pair repulsion. Now, what does that actually mean? In order to understand what valence shell electron pair repulsion means, let's consider the water molecule. The water molecule has one oxygen with two hydrogens attached to it, but it also has these pairs of electrons here. If we remember from electronic configurations, two electrons can share an orbital together. And so these two electrons would be in one of oxygen's orbitals, but these two would be in a different orbital. So we could say that we have these two orbitals right here. Well, both of these orbitals, what kind of charge would those have? Those would both have a negative charge. And the bond between hydrogen and oxygen, that's going to have some electrons in it as well. So those are going to have a negative charge. Well, all of those negative charges want to repel each other. And so these molecules are going to be arranged in such a way that all of these clouds of electrons, all of these negative charges, are pushed as far away as they possibly can. And that's really going to depend on how many bonds each molecule has. So what do I mean by how many bonds it has? When we look at this chart over here, we see this word domain. What is a domain? Well, an electron domain is going to be any area where I have electrons. So for H2O, I have 1, 2, 3, 4 areas where I would have electrons hanging out. That would be 4 electron domains. But if I look at something like CO2, my first example up on the chart, CO2 would have 1, 2 areas where electrons are hanging out. Because this double bond is basically right on top of itself. So I've got a single bond here and then a double bond right on top of it. And so that would be one area of electron density. So we have 2 electron domains in CO2. And so that is going to play a significant role in the shape of these molecules. And that's going to be the general gist of how we figure out what is our molecular shape going to be. Our big focus in Vesper diagrams in first year general chemistry is going to be being able to draw them out, okay? And so in order to draw these out, I'm going to just consider the electron domains. So for CO2, I'm just going to draw a line for the electron domains, and I'm going to draw them as far spaced out as I can. So CO2 is going to take on this exact linear geometry. Notice I've got this bond angle section here. Well, for CO2, because it's going to be trying to take on those 2 bonds as far away from each other as possible, it's going to get this bond angle of 180 degrees. Because that's how far it's going to be able to push them apart. Now this H2O, that's going to have a different bond angle because it has 4 domains, and we'll get there. So that's going to be CO2. What if I had one area that was bonds and one area that was just lone pairs, like an N2? Well, in that case, I'm just going to draw this like this. Nice and simple, nice and straightforward. It's still going to have that linear shape. It's still going to have, you would call that 180 degrees between this bond and the electron pairs that would be over here. But we don't care about the triple bond in this case. We only care about the shape. That's what Vesper diagrams are really going to be focused on, is about that shape. If I get into 3 electron domains, well then I'm going to start looking at a trigonal planar shape. So let's look at CH2O. This is the Lewis diagram for CH2O. Now, right off the bat, we should be able to notice I have three areas of electron density. Three areas of electron density. So if these were trying to be as far apart as they can, these hydrogens, those should really move over. Those would want to move away from that oxygen bond. But they wouldn't want to move too close together. And so I'm going to redraw this as the Vesper diagram, where all I care about is the molecular shape. I'm not caring about how many bonds each of these is. I only care that this is an electron domain. So here's my 1, 2, and 3. 1, 2, and 3 electron domains. So we call this trigonal planar because it makes a triangle, and if I look at it from the side, it would just be flat. And so the bond angles there are going to be 120 degrees, because that's as far as I can get away from each other on each of these bonds. So each of these bonds is going to be 120 degrees away from each other. So that's what we mean by those bond angles. Okay. So that's going to be 3 domains. Let's draw that one in here. Now, what if I had NOH, where I have an electron pair? Well, NOH would look like this. But notice, I've got a domain here, a domain here, a domain here. So I've got 1, 2, 3 domains. Well, these 3 domains would push each other apart. So I would again have this bond angle here, this angle right here, this would be 180 degrees. And I'm not drawing in the electron pair because the electron pair doesn't take up very much space. And so as far as we can consider, it's still going to push these away, but it's not going to have a big role to play in these atomic interactions. And so I can draw this structure up here. This is going to be my bent structure. And then the O2, this is going to take on a very similar structure as the N2 did. It's really just going to have this O bonded to an O. And it's got 3 electron domains, but 2 of them are just lone pairs hanging out over here. So it's still going to have that linear shape. So nothing extremely special. So far, the only big special thing we've seen is this bent structure for the NOH. But once we get into 4 electron domains, we're going to have to start utilizing a 3rd dimension. And that's where Vesper diagrams really start to help us out. We're going to need to be able to draw these in a way that we can see on flat paper that there are 3 dimensions to a molecule. So let's start with CH4. CH4 is going to be methane. It's going to be carbon surrounded by 4 hydrogens, and these are all going to try and push each other away. And you might be thinking, well, Chesky, these are already pretty far away. It's already 90 degrees. How could they be any farther? Well, if we utilize the 3rd dimension, one of these hydrogens could come out of the page and one of them could go into the page. This hydrogen could come out towards us, move up, and this one would go in, and we would actually get a further spacing than 90 degrees. We'd actually get 109.5 degrees. And so if we draw that, we can draw 2 of them pretty easily, just one going straight up, one going straight out to the right side here. But then I need to draw these other 2 with one coming out of the page and one going in. And we do that using this technique where we draw a wedge for the molecule that's coming out, for the atom that's coming out. So we wedge, we wedge out, like vegging out. And then the other molecule going into the page, we use a dashed line to represent that. And so we wedge out and we dash in. And so the bond angles between these end up being 109.5 degrees. And so that's going to be quite a bit more room. So the first shape we have there is going to be a tetrahedral. So whenever we have 4 domains, and all 4 are taken up by atoms, we are going to have this exact drawing. So whenever you see a molecule, you need to draw the Vesper diagram, you're going to take this model and you're going to draw the same thing, just using different elements. As long as you have all 4 of those domains being bonds. So now let's look at NH3. Once again, that's going to be having that extra electron pair. So if we just draw this out, it's the Lewis structure. We see those are separated like that, but in Vesper diagrams, we want to highlight, we want to pay emphasis to that three-dimensional structure. And so once again, we use the wedge out, the dash in to show that. And then we would have an electron pair up here that would be repelling those. All right, and then H2O. We already have this drawn over here. This H2O, that's going to have those four domains. It's going to have two that are locked up in a chemical bond and two that are just lone pairs hanging out on the side. And so we're going to have H2O forming that bent structure. That's going to be hugely important for water. And then finally, for something like HCl, where it is just one bond, it's going to look just like these did up here. So notice, every time I only have one electron domain, one bond for my domain, then I'm just going to have this linear structure. It's very straightforward. So now let's talk about this category right here, this hybridization. What is that referring to? Well, when we talk about covalent bonding, we have an overlap, we have a sharing of electron orbitals. And so if we think of this CH4 here, the CH4, carbon is going to have an electronic configuration for 1s2, 2s2, 2p2. That's going to be its electron configuration. This 1s2, that's going to be really close to that nucleus. That's going to be locked up on the inside, and it's not going to be used for bonding. We only use the outermost shell for bonding. So we could say we have access to the 2s2 and the 2p2. When we bond, notice carbon's making 4 bonds. It only has 2 orbitals. Really, only 2 orbitals. Well, when we bond, these 2 orbitals are going to actually spread out and share all of that space around that carbon atom. And so I've got, really, because I've got that circle structure for S, and I've got those 3 options for the p orbitals. Since I've got those 3 options for the p orbitals, I could say I've got an S, a P, and a P. These are all able. I can have these merge together in any order that I want to. And they're going to. When I have these 4 electrons that need to suddenly spread out so that they can form these bonds, all 4 of these are going to merge together. And we call that a hybridized orbital. And so when I have these 4 electron domains, all of those orbitals merge together into something called an sp3 orbital. 1 s orbital, 3 p's that have merged together. Now, if I only have 3 electron domains, well then the first 3 electron orbitals merged together, and the last one was just left alone. And so we say that's sp2. Notice, I've got S, P, and P here. That's 3 letters for 3 domains. Here, I've got S, P, P, P. That's 4 letters for 4 domains. And so what do you think I'm going to have for my 2 domains? For this is just going to be SP, 2 letters for 2 domains. So when I have that hybridization for something like CO2, what's really going on here is the carbon hybridized an sp orbital on either side of it. So it has this electron cloud on either side of it. And those oxygens came in, and they also shared their electron clouds with that carbon. And so they've got these 2 electrons being shared. But since they make a double bond, then those extra p orbitals for that carbon, those 2 leftover p orbitals, let's do those in a different color. Those 2 leftover p orbitals are going to be shared over the top. They're going to take on this shape here. So at the end of the day, we should be able to take a formula like CO2 or CH2O, and we should be able to make the Lewis structure for that, and then use that Lewis structure to identify the number of electron domains on that central atom, and then redraw the Vesper diagram. We should also be able to identify the hybridization type of that central atom. So for this carbon, that's got an sp hybridization because it only has 2 electron domains. For something like this NH3, that has 4 electron domains because it has that extra electron pair that we just don't draw in here. And so that is going to be sp3. The bond angles, it's okay if we don't have those memorized, but we should have the hybridization down.